Let's take a look at multiplying and dividing complex numbers. Firstly, let's do multiplying. So it's easy when the complex numbers are written in Cartesian form. If z equals 3 minus I and w equals 5 plus 2i, multiplying them, you can just use the normal rules of algebra. Then z times w, or zw, is just simply 3 minus I times 5 plus 2i. Okay, and expand the brackets. So you get 15, and then you've got 6 minus 5 for the I component. 6 minus 5 is 1, so plus I. And then the final part, you've got minus 2i squared. Okay, so if you want to do this quickly, it's really just the first two terms and the last two terms multiplied. Okay, so you've got 17 plus I. Now, if they were in polar form, you're going to have a problem. So if you have z equals 2 cis pi on 3, and we're going to use radians here, as they normally will be given. W equals, let's do 4 cis pi on 6. Okay. So you might be thinking, why don't we just convert them into Cartesian form and then just multiply it? And then we can change it back to polar form if we have to. So that's one way to do it. Okay, so let's just have a quick look at the answer. So if we do convert it, we're going to get 2 cos pi on 3, right? So that's the real part. Then we're going to have the imaginary part, so I'll just call it plus I, and this will be 2 sine pi on 3. Remember that cis means cos, imaginary number, and then sine. This will become pi on 3. Okay, so here that's cos, that's 1 on 2, so 2 times 1 on 2 plus I times 2 times root 3 on 2. You'll get good at trigonometry by doing these. Okay, so overall that's 1 plus root 3i. For the w, this is 4 cos pi on 6 plus I times 5 sine pi on 6. Okay, so let's continue on. Cos of pi on 6 is root 3 on 2. And sine of pi on 6 is just 1/2. Okay, so you've got an overall of 2 root 3 plus 2i. So now when I multiply them, 1 plus root 3i times 2 root 3 plus 2i. Let's do this the shortcut way. So 1 times 2 root 3, this is the real part, so you got 2 root 3, and then this will be 2 root 3, but subtracting because you got I squared, right? So you got minus 2 root 3. This is interesting. So there's no real part. Imaginary part, I've got 2 and 2 times root 3 times root 3, which is 2 times 3, which is 6. Okay, 6. So the final answer is just 8i. Now, that was unexpected. That's not always the case, okay? So this is just a coincidence. Let's have a quick look at what it looks like on the Argand diagram. Maybe we can see something unusual about this. 2 cis pi on 3, okay, so pi on 3 is about 60 degrees. This is about 60-degree line, okay? Okay, there's 2 units there. So this angle here is pi on 3. Then I need another complex number. I just call that Z. So the another complex number 4 says pi on 6. So pi on 6 is about here. I want 1, 2, 3. Okay, 4. So this one is W. This is pi on 6. Alright. So I'll just mark them in with 2 colors. There's Z. Okay, there's W. And our answer is 8i. So 1, 2, 3, 4, 5, 6, 7, 8. What's the relationship between the Z, so this direction here, and this W here? Can I say that the length of the final answer is the product of these two? So this has a modulus of 2, or a length of 2, and this has a length of 4, and this has a length of 8. Wow, okay, that gives us an idea, perhaps, that we can just multiply the modulus to get the overall modulus. Cool. But how do I know where to draw this direction? I mean, do I just add the angles? I mean, it looks like it's rotating in that direction. Possibly. And in fact, that is the truth. So when you multiply complex numbers, the modulus get added. Modulus add. But the not add, multiply, I beg your pardon, multiply. And the argument is add. Okay, we're going to write this formally as a property in a moment, but let's just try this method without using this complicated process of Cartesian form. Okay, so I could just start with these two, and then I can just conclude ZW is the product of the two moduluses. So it'll be 2 times 4. I'm just writing this out so you can see the working. And then cis, and then I add the angles. Okay, so pi on 3 plus pi on 6. Okay, so 2 times 4 is 8. And pi on 3 plus pi on 6 is actually pi on 2. Okay, just give yourself a moment just to check that out. That is pi on 2. So I hope you can see this answer here in polar form is the same as this answer here in Cartesian form. I remind you, 8i. I've just drawn it as 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's 8i. 8 cis pi on 2. That means go around with an angle of pi on 2 and a length of 8, which is exactly there. Anything with an argument of pi on 2 means the number is purely imaginary. Okay, that's what they will say. Purely imaginary means there's no real component. Interesting, isn't it? So on this point here, if you didn't see that, you could still expand it. So you could write 8 cos pi on 2 plus I times 8 sine pi on 2. Cos of 90 is 0. And then sine of 90 is 1. So you've got 8 times 1, which is 8. Okay, so that's another way to confirm. Alright, let's write these as a summary of the properties for multiplying. Multiplying complex numbers. You should use polar form. Okay, So z times w equals the modulus of z times the modulus of w. Cis, and then it's the argument of z plus the argument of w. Okay, so before we use the symbol theta, so you could call it theta 1 and theta 2. Sometimes I like to write the actual letters ARG to represent argument. Okay, and you can also write the modulus of z as mod z and then mod w. In general, you can actually just know that you just multiply all the modulus. So if you had 3 complex numbers, by the way, so if you had z1 times z2 times z3, then it's just the product of the 3 moduluses. So you can have modulus of z1, modulus of z2, modulus of z3, and then cis, and then you add the arguments. So you have theta 1 plus theta 2 plus theta 3. So on a diagram, what happens is the lengths get multiplied, but the angles get added. Okay, so it actually rotates the number around the complex plane. I haven't talked about how the complex number is represented in terms of a rotation, as we don't have time to discuss this, but you may find this as you're doing investigations. Alright, so now we have to quickly go to have a look at the other side, which is division. Now, dividing has a very similar property, but there's one thing to note with division in Cartesian form. It is useful to know something called, well, I call it realizing the denominator. Okay, so you might have heard of something called rationalizing the denominator, which is what we are essentially doing, but we're making the denominator real. Okay, so let's have a look at this. So let's try this again as an example. We can actually use the same complex numbers we had previously. I'll just have a quick look. I think it was, there we go, 3 minus I, and w equals 5 plus 2i. Alright, this time let's do z divided by w. So we're going to write 3 minus I over 5 plus 2i. Now you could leave your answer like that, but it's not good to have an imaginary value on the denominator. So we multiply by the conjugate. So we multiply by 5 minus 2i over 5 minus 2i. And then the top part, you'll get 3 minus I, 5 minus 2i. On the bottom, you get 5 minus 2i and 5 plus 2i. Notice that's difference of 2 squares. We're going to utilize that property that we learnt before. Firstly, let's multiply the top out. So we got 15. And then going for the 2 end terms, so that's plus 2. Okay. I beg your pardon, it should be minus 2 because you're going to get plus 2i squared. Okay, which becomes minus 2. So that's the real part. The imaginary part is going to be negative 6 and negative 5, so negative 11. Okay, down here I'm going to get 5 squared plus 2 squared. Okay, remember that? So let's keep going and resolve this. We've got 13 minus 11i all over 25 plus 4 is 29. So if you want to separate it out, you can say that's 13 over 29 minus 11 over 29i. Okay, so that's the real part, that's the imaginary part when you divide the two together. So now, if we look at the example using polar form, This is different set of complex numbers, but we'll use the same values from the previous question. We've got z equals 2 cis pi on 3 and w equals 4 cis pi on 6. Now, it's good to note that I'm going to be dividing by the smaller argument. If it was the other way, you're probably going to notice that you have a negative overall argument. Okay, I'll show you what I mean by this. So we're going to find ZW. So we're going to write it as 2 cis pi over 3 divided by 4 cis pi on 6. So at this stage you don't know what to do, but a good guess would be we can just divide the modulus. Okay, so 2 divided by 4 is a half, and the arguments we just subtract them. So pi over 3 minus pi on 6 is just simply pi on 6. Okay, you can check that yourself. And that's it. So that's the answer in polar form. If I wanted to write that in Cartesian form, I can expand this out. So this will be a half cos pi on 6 plus I times a half sine pi on 6. Okay, remember cos pi on 6 is root 3 on 2. So 1/2 times root 3 on 2. And then sine of pi on 6 is 1/2. So overall the answer is root 3 over 4 plus I, 1 over 4 times I, okay? Alright, so you have two ways of writing the answer. You can do it in the polar form, or you can do it in the Cartesian. Okay. So lastly, if you want to have a look at it in terms of the diagram, I think it's starting to become more understandable what happens with complex numbers. Okay, as you investigate this more and more, you'll get a better understanding of what actually occurs. You do need to know this for some of those harder questions in the IB exam in section B. That will rely on you understanding the geometric representation of complex numbers. So 2 cis pi on 3, we drew this before, 1, 2, and then 4 cis pi on 6, 1, 2, 3, 4. This is very rough, by the way. Okay, so this is W, this is Z, and then the final answer, I'm going to use Cartesian form. Actually, I'll use polar form. It happens to be on the same angle, but shorter, so half. There, that's Z divided by W. And because I'm starting from Z and I'm dividing by W, what's happened is I'm reducing my length of Z by a factor of W. That's why 2 divided by 4 is a half. And the angle got reduced, so it got subtracted by that amount. That's why it happens to be in line with W. If I did it the other way, if I went W divided by Z, then I have to reduce the angle of W by a factor of Z, which means it would be in this quadrant, okay, in the negative section. And my modulus would be a bit larger. Okay, so let's summarize that property. We've got multiplying complex numbers. We multiply the modulus, we add the arguments, and then finally we can squeeze this in. So if we're dividing, you get Z on W equals the modulus of Z over the modulus of W cis, and then the argument of Z minus the argument of W. Alright, so that's simply how to multiply and divide complex numbers. definitely use polar form. Don't use Cartesian form. Only use Cartesian form for adding and subtracting. And learn how to convert between the two forms. You need to readily be able to do this quickly without too much effort, and use your understanding of trigonometry and vectors to help you do this process quickly.